In 41 through 49, let x and y be sets. Let a and b be any subsets of x, and let c and d be any subsets of y. Determine which of the properties are true for every function f from x to y, and which are false for at least one function f from x to y. Justify your answers. For all subsets c and d of y, if c is a subset of d, then the inverse image of c is a subset of the inverse image of d. So that's saying if you have a collection of outputs, and you consider a subset of those outputs, then the corresponding inputs to that subset are going to be a subset of the original inputs corresponding to the original set of outputs. That sounds a little confusing. It is true. You can test it a couple times. I'll save you some time though, and we'll jump straight into the proof. If this is wrong, then we would be proving something false, and that's impossible. So we'll end up in a roadblock anyways if this is false. Let's try to prove it. Now, this is an if-then statement. We're going to approach this with a direct proof, which means that we're going to assume the if part, and then we're going to conclude the then part. So let's start by assuming that C is a subset of D. Now, our goal is to show that the pre-image of C is a subset of the pre-image of D. We're trying to prove that something is a subset. To do that, we can use an element argument. We can start with an element from the first set and show that that element must therefore be in the second set. Let's start with an element from the first set, which I'll call lowercase r. Now let's first talk about what the set even is. This is the set of all elements, x in x, such that capital F of x is an element of C. Now r is an element of the set, so we get a couple things about r. First, we can say that r is an element of x, capital X. We can also say that capital F of r is an element of C. We get that any element in the set, lowercase x, has the property that the corresponding output is an element of C. So since r is in that set, then that means r satisfies this property, where in this case r is actually the x here. So capital F of r is an element of C. Now we know something about capital C. Capital C is a subset of capital D. That means every element in capital C is also an element of capital D, including this element, capital F of R. Capital F of R is an element of capital C. So since C is a subset of D and F of R is an element of C, then capital F of R must also be an element of D. Now, we're almost there because since capital F of R is an element of D, to draw our final conclusion, let's remind ourselves what this even means. This is the set of all, I'll use lowercase d this time, that's an element of x, such that capital F of D is an element of capital D. So this is the definition of capital F inverse of D, or otherwise called the pre-image of capital D. This is the set of all elements in the domain such that the corresponding output is an element of D. Now here we have an element R, which is in the domain, and we know that the output is in D. That's precisely what needs to be shown in order to show that lowercase r is an element of capital F inverse of D. And so we started with an element in capital F inverse of capital C, or the pre-image of C, and we ended by showing that this element must therefore be an element in the pre-image of D. And ultimately, we use the fact that C is a subset of D in this proof. And so that proves that the pre-image of C is a subset of the pre-image of D. Thanks, everyone, and I'll see you in the next video.